In the latest data analysis of the cosmic microwave background, an international team of researchers found something unexpected. They measured an unusual alignment of temperature fluctuations from one region of the sky to another. This has shocked some scientists who say it challenges our fundamental assumptions about the nature of the universe. And other scientists are saying it's probably nothing. Let's have a look. It's not like I haven't warned you about this before. The universe might be a simulation. In fact, it very likely is a simulation, at least if we believe the late great Stephen Hawking. But don't worry, there's no danger that you'll be unplugged. You see, if our universe is a simulation, then it's extremely likely that it's a simulation within a multiverse. And in a multiverse, there are lots of other universes besides ours. So if it is a simulation, it doesn't matter whether you get simulated or not because you wouldn't notice it, so relax. But joking aside, if the universe is a simulation, then it's not just a simulation, it's a simulation with bugs. Because the new result from the international team now is that they found an unusual alignment of temperature fluctuations in the cosmic microwave background from one region of the sky to another. That is something you'd expect if the universe is not only a simulation, but a simulation with bugs. You see, according to our current theories, the universe is both uniform and isotropic. Isotropic means that it looks the same in all directions. The reason that we can assume this is that the cosmic microwave background, which is the radiation left over from the Big Bang, fits remarkably well with the predictions from a model in which space is perfectly homogeneous and isotropic. The idea is that the universe was created in a hot, dense state and then expanded and cooled down. As it expanded, the radiation stretched with it, and that's why today we observe it in the microwave range. This works really well. It explains the overall features of the cosmic microwave background quite accurately. For example, there are tiny temperature differences in the cosmic microwave background, and that's what we call the cosmic microwave background anisotropies. But now comes the new study, which is just published in the journal Physical Review D. In this study, the international team looked for correlations between temperature fluctuations into different regions of the sky. And what they found is that the fluctuations are strongly aligned with each other. Technically, they measured what's called the bispectrum of the cosmic microwave background. The bispectrum contains information about how the temperature fluctuations correlate with each other. And in the new data analysis, they found a signal that they say has a 99.99% significance, so it's very unlikely to be a fluctuation. The problem now is that this alignment of temperature fluctuations can't possibly come from a homogeneous and isotropic universe. At least not without violating the known laws of physics. That's because if you have a perfectly homogeneous and isotropic universe, then the statistical description of the temperature fluctuations is what's called a Gaussian random field. A Gaussian random field is basically a field where the probability distribution of the fluctuations around any point is a normal distribution. That's a bell curve. Now, technically, the distribution of the temperature fluctuations in the cosmic microwave background isn't exactly a Gaussian, but it's close, and that's why I'm simplifying here. The crucial property of a Gaussian random field is that all higher-order correlations vanish. That means if you want to measure correlations of higher order than 2, then they're 0. That's just how it works mathematically. Mathematicians have known this for a long time. Physicists also know this because they confirmed it experimentally. The new measurement of the bispectrum now shows that the correlations are non-zero. And that's a problem. Physicists are now divided. Some say it's just a statistical fluctuation, though they admit it's a very unlikely one. And others say it as a profound signal that tells us that something is wrong with our models of cosmology. It could be that the universe isn't as homogeneous and isotropic as we think it is. Or it could mean that there are new particles or new fields that we haven't yet detected. It could also mean that the entire universe is a simulation with bugs. Okay, maybe not that last one. Though what's interesting is that similar measurements in the past have led to a lot of discussion about inflation. This is the idea that the universe didn't start out with a big bang, but that it underwent a period of very fast expansion in the first tiny fraction of a second after its creation. Inflation solves a number of problems with the standard model of cosmology. For example, it makes the predictions of the model fit better with observations. However, inflation isn't a scientific theory. It's more of a toolbox with various models that can all fit the data equally well. So people use whatever model fits best and then claim that this particular model of inflation is confirmed. Not surprisingly, this has led to a lot of criticism. One way to indirectly test the idea of inflation is to look at the statistics of the temperature fluctuations in the cosmic microwave background. If you believe that there was a period of very fast expansion in the early universe, then you expect certain non-Gaussian features to show up in the statistics. And such features have been looked for in the past. The results were inconclusive. The new result is interesting because it's the first measurement that clearly contradicts the Gaussian hypothesis. So what do we make of this? Well, first of all, I'd like to remind you that correlation doesn't mean causation. Just because you find a correlation between two things that doesn't tell you anything about the cause. It could be that the temperature fluctuations are correlated because they come from the same source, or it could be that there's a third variable that causes both. In this case, the third variable could be inhomogeneities in the matter distribution. In a recent paper, for example, the authors of a different study claimed that they found a correlation between temperature fluctuations in the cosmic microwave background and large-scale structures in the distribution of galaxies. The issue with this earlier paper was that it was very difficult to exclude the possibility that the signal came about because of dust in our galaxy. The new study now used data from the Planck satellite, which observed most of the sky at millimeter wavelengths where dust doesn't absorb much, so it's much clearer than the earlier studies. But it still leaves open what might be the cause of the correlation. The authors of the new paper say that their result is robust against all known systematic errors, but they don't comment on the possibility of a third variable. I think we need to keep in mind that looking for correlations in cosmological data is a bit like looking for a needle in a haystack. The difference is that the needle is made of spaghetti and the haystack is made of Swiss cheese, so keep that in mind. On the other hand, it's certainly true that the universe isn't just a bunch of dots. Galaxies form structures. There are filaments and sheets and voids. So it's natural to ask whether this structure has a counterpart in the distribution of the cosmic microwave background. Indeed, a few years ago, a group of physicists claimed they found a signal for that. They said that they detected a kind of gravitational lensing in the cosmic microwave background, which comes about because matter in the universe isn't distributed homogeneously, but tends to clump together. What's interesting is that the signal they found resembles a prediction from a class of models for inflation, though it's somewhat weak compared to the predictions. Still, it was the first time that an inhomogeneous model of the universe fitted the data better than a homogeneous one. So this was quite a sensation. Then again, it's also true that the signal they found was very weak and other groups couldn't confirm it. And indeed, if you look at the data closely, then the signal is gone. Now, this doesn't mean that the universe is homogeneous, because that would require showing that the signal is gone in many different data sets. But it does mean that if there are inhomogeneities, then they must be really smooth and really weak. Let me finish this video with a thought. You see, there's another way to create an apparent correlation between temperature fluctuations in different regions of the sky. You could have regions that are really similar because they came about from the same source. The issue is then that if they came about from the same source, then it's unclear why they should be aligned. If they came about from different sources, then it's unclear why they should be similar. I think this hints at the possibility that what we observe is a rare fluctuation, but not necessarily a fluctuation of fundamental constants or particle physics or something like that. It could be a fluctuation of the multiverse. Welcome to the channel. Thanks for watching. See you tomorrow.